Hi, my name is Chase Fiore, and I wanted to give you a quick overview of my very first Dynamo project that I've been working on. I'm quite proud of it. So I had two telephone poles that I needed to be able to string cables between. Now in Revit, if I just do 2 points and I attach a spline, I can fake a catenary, but it's always going to be a parabola and not a true catenary. So what I wanted to do was be able to pick 2 points in 3D space and then apply tension to a cable and be able to art direct it as much as I want. So that's exactly what I have here. I have an input of 2 XYZ coordinates, and then I have this A value, which is actually the forces of gravity working upon the cable. So as I increase this, it's going to make it more tense. If I decrease it, I can make it slack to the point that the cable will basically no longer make any sense. So if I leave this at a more reasonable number, I'll walk you through how this actually works. So we have our inputs. Our inputs go to this quick little check. This check it makes sure that x1 is always less than x2. If not, it'll just reverse all the x and y's before it passes it on to the other calculations. That way we're always working in a positive direction for the calculation of the catenary. So how it works basically is that you have your x, y, and z of this point, you have your x, y, and z of this point, and the first thing it does is it calculates the slope between the 2 points. And there's a good reason why it does that. Basically, once I apply the actual catenary curve to it, these points are going to want to shift either upward or downward, depending on the value of this A. So if I know the slope to begin with, then I can take all of these points and I can just offset the Z for each one of these calculated points. Now we get to those by doing this little point spacing calculation here. So you input your X range and it outputs a list of points, and then the Y points come in, and this just makes sure that the length of the two lists is always equal. So once we have that, we can calculate for every X position, because at this point we really don't care about Y. We're going to account for Y later. But for every X position, what is the Z location of this point? What should it be? And so it does that, it calculates those, and it does that by mirroring the two distances that you inputted at the beginning between 0. So it'll take your 2 points and make sure that it's always the same positive and negative value of both. And then later on, we actually come back here and where is it? This is the Y offset. So that's actually just turning this in whatever Y direction that you calculated at the beginning. And it does that by also calculating the slope of every point, but in the different plane. What was I saying? So we calculate the Z direction for all of these. It outputs this list. It accounts for the change in Z direction because you adjusted this A value, and then it combines all 3 of those coordinates into a single list. This just makes the nice curve between them so that I can see what's going on. And then this is the part that took me a really long time to figure out, and it turned out to be one of the simplest things to do, but it's one of those things where I hadn't worked in the program before, so I didn't know what this little list subsets thing did, and that was the magic key. So what I wanted to do was to take a Revit family. In this example, I created a 3-point adaptive component, and I wanted to translate that to every single point. So the adaptive family is going to take a very specific list of points. You can see that here, these lists of 3. So it will take the first point, apply the first point in the adaptive here, the second point there, and the third there. Now, if I didn't have this list subsets thing, it would do every other group of 3. So you would have a space between each one. Now, if I didn't use a 3-point adaptive component, if I used a 2-point adaptive component, you'd have straight lines between each one, not a nice smooth curve. That's why I went through the extra effort to try to figure this out. So basically, this list subsets takes your incoming string of x, y, and z values, breaks it up into these nice little three-dimensional list, but it takes this last value and it repeats it again and then continues the list. That way you have an uninterrupted chain of families. Now, if I put this back on manual and I run it, it will take a second because this is actually going to place all of the families along the rope. You can see that the adaptive components have been applied to every third point in space. It's nice and seamless. They make a perfect arc. This family I made is just a rope, so it's actually a spiral shape when you go to render it. And yeah, that'll work for any point in three-dimensional space, and you can change it to your heart's content, and it is very rock solid at this point. So thank you for watching this video, and hopefully I'll come out with a couple more. I've worked on some other adaptive components as well that I wanted to document and show you my thought process. Thanks.